Hi everybody, how's it going? So today we're going to solve LeetCode 36, valid Sudoku. Now this is a very famous interview question. It's also a medium question, and it's a fun one. So this question gives you a 2D board, a Sudoku board, a 9x9 grid containing 81 cells, and you should determine whether that Sudoku board is valid according to some rules. So if you don't know the Sudoku game, it's really easy to learn. I would advise you look it up real quick, or I'm just going to quickly read the 3 rules that we're going to follow in order to determine whether a Sudoku board is valid. So a Sudoku board contains rows and columns, and each row must contain the digits 1 to 9 without repetition. Each column must also contain the digits 1 to 9 without repetition. And in the overall grid, we also have subgrids. We're going to call them subboxes. We have 9 subboxes. You can see them here. This one is a subbox, 2, 3, 4, 5, 6, 7, 8, 9. And these ones should also contain the digits 1 through 9 without repetition. So for example, we do have a 5 here. In this particular row, there should only be 1 5. In this particular column, there should only be 1 5. And in this subgrid, there should only be 1 5. Now let's make this example a little bit bigger so we can visualize it a lot better. Alright, so we have the following Sudoku board. Now what we're going to do is we're going to determine whether or not this board is valid. So for us to determine whether or not this board is valid, we have to follow 3 rules. First rule is a number should occur only once in the row that it's part of. So for example, we do have 5 here. I'm going to circle it. 5 should occur only once in this row. It should not be repeated. And also, the second rule is a number should occur only once in the column that it's part of. So 5 should occur only once in this column that it's part of. And also, a number should occur only once. That's the final rule. It should occur only once in the subgrid that it's part of. The subgrid is this one. This is a subgrid, and we have 9 of those. We have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 5 should occur only once in this subgrid. In this case, 5 is a valid placement because it occurs only once in this row, in this column, and in this subgrid. So we're going to do that check for every single number in this Sudoku board. Back to the question. A few things to note, however, is that we're going to have empty cells. We're going to have boards that are partially filled, and those could be valid if they have numbers that appear only once in like rows, columns, and subgrids. So the board doesn't have to necessarily be completely filled. And only the filled cells need to be validated according to the mentioned rules. So empty cells would be represented with a period like this. And yeah, there it is. So how do we solve this question? Well, this is a pretty standard iterative question. What we're going to do is we're going to iterate through the entire board, and whenever we get to a particular number, we're going to check if that number occurs more than once in the row that it's part of, in the column that it's part of, and in the subgrid that it's part of. And we're going to do this in a very smart way. What we'll do is we're going to initialize an array of hash maps representing every single row, every single column, and probably every single subgrid. I'm saying probably now because we're going to get there later. We're going to have a hash map that represents the first row, and in this hash map, we're going to map numbers to how many times they occur in this row. So while we're iterating through this row, if we come across 5 again, say here, then we'll know that we've seen 5 twice, and then we can just return false. Also, when we're iterating through this column, if we come across 5 somewhere in this column, we know that 5 occurs more than once, then we can return false. So that's it. And we're going to do the same thing again for the subgrid. As always, it's going to be really simpler to explain as we go through the code, so bear with me as we go through the code. So what's the time and space complexity of this algorithm? Well, for time complexity, we're going through every single row and every single column. So that would arguably be O of row times column, but we already know there are at most 9 rows and 9 columns, so that's a total of 81 cells that we're going to go through. And in big O notation, we draw constants, so time complexity is technically O of 1. And then for space complexity, also we're storing an array of hash maps that are going to have a finite amount of values in them, because the hash map for row 1 can only take at most 9 elements, and all of those can only take at most 9 elements. Each column can only take at most 9 elements. Each subgrid can only take at most 9 elements. So we already know that there's a finite amount of values that can be stored in the hash maps. So those things are constants. And in big O notation, we drop constants. So space complexity is O of 1. So that's it. That's it for this question. Let's dive into the code. Alrighty. So the first thing we want to do is create an array of hash maps representing every single row and every single column. So, oh my god, map. We're going to map integers to integers, and that's going to map a particular number and how many times it occurs. So this is going to be an array. Let's call it rows is equal to new hash map. And we're going to have 9 of these because we have 9 rows. And then we make another one, integer to integer, columns, new hash map. And then we're also going to have 9 of these. And then we make another one for the boxes, the subgrids. So now that we have that, let's initialize every single hash map for each row and each column with like an initial empty value. So let's say for int I is equal to 0, I is less than 9, 0 most, I plus plus, and then we say for rows of I, that's for rows of 0 through 9, this is equal to new hash map, and then this should be integer, integer. And then we do the same thing for columns and boxes. Okay, I feel like I should add some comments, so I'm just going to say initialize, is that how you spell it? Initialize one hash map for each row and column and box. Subgrid. So under the hood, this is what's happening. We're creating an array of hash maps, kind of like this. So if you visualize it, so we have like an array containing hash maps with key value pairs. So for row 0, that's for the first row, we're going to have key value pairs. Say for the integer 5, how many times it occurs, for the integer 6, how many times it occurs, and then say for example, second row, that's row of index 1, same thing, row of index 2, third row, same thing. So this is what's happening under the hood. Now let us iterate through the entire board and then check how many times each number occurs. So we say for integer I is equal to 0, I is less than board dot length. So I represents the rows I plus plus, and then we do for integer j is equal to 0 is equal to 0. J is less than board of I dot length. Then we can just say j plus plus. Also, we can straight up just say 9 because we know we're given a 9 by 9 grid, but I kind of like it this way. And then let's get the current character that we're looking at. So let's get character, let's call it current. That would be equal to board of this row and this column. So now that we have the current character, we need to make sure that it's not empty. And empty characters are represented by a period, so if something is not a period, then we know it's not an empty character, it's actually a number. So if current is not equal to period, then it's a number. So we can convert it to like an integer, that would be integer of current. Cool. Alright, so now we can update how many times we've seen this number in this row and column. So how do we do that? we can just say rows of I, rows referring to this map here, I referring to the particular, referring to this array, I referring to the particular index of the hash map that we're looking at, and then we're going to put, what are we putting? We're putting this number, and then what's going to be the value? Value is going to be whatever is in there if we already have something in there. So map.get or default. I hope that's how you spell it. We're going to get the number. If it's not there, we just return 0. If it's there, we add 1 to it. So that's it. And we're also going to do the same thing for the columns. So copy it. And this is going to be columns of j. It's not going to be I because I represents the rows. It's going to be columns of j to put. It's going to be columns of j again. That's pretty much it. Cool. So now that we've taken care of these two cases, I'm going to get to the third case in a bit. It's going to be easier if I do it last. So now that we have this, what we can do is we can check how many times we've seen this number in this row and in this column. What we've done here is we've just updated the number of times it occurs. We haven't really checked whether it's duplicated. So checking whether this number is duplicated. So we can say if rows of I that get num, if this is greater than 1 at the number of times it occurs, if it's greater than 1, then we know it's duplicated. Or if columns of j that get num, that's a particular number, if it's also greater than 1, then we know that it's duplicated. If this is ever the case, what we do is we just return false. And what we've done so far is effectively going to check whether this particular number is duplicated in the row and in the column that it's part of. Now, how do we check the subgrid? There are two ways to do this. Oh, I'm sorry. There are a ton of ways to do this. I've only tried 2 of them, and one is faster than the other. So I'm going to do the faster one first. And surprisingly, the one that's faster actually has more lines of code than the one that's slower. So for the faster one, what happens is we're going to calculate like where this grid starts. What's the start index of this grid? What's the start row and what's the start column? And then we're going to iterate through that grid. Because we know that that grid is a 3x3 grid. It has 3 rows and 3 columns. So we're going to iterate through that grid because we already know where it starts, and then we're going to check whether we've seen this number in there. So I'm going to say this code is theoretically faster. So let's say int, let's call it grid start, also subgrid start. So how do we determine the start of the subgrid? Well, it's a simple formula. We just do row divided by 3. That's going to offset the row. And then we multiply it by 3. And then we do the same thing for the subgrid column start. So this should be subgrid row start, and this should be the subgrid column start. And that, you guessed it, j over 3 times 3. Now, what's happening? Let's go back to the example. Okay. Stay with me now. So imagine we're iterating through the board and we're currently at the cell. And this cell has a value of 8. And this cell is at row 2, column 2. But the subgrid that this cell belongs to starts at row 0, column 0. That's where the subgrid starts. So we want to get, sorry, this should be 0. Row 0, column 0. So we want to get the start index of the subgrid. We want to get where the row starts and where the column starts of this particular subgrid, because we want to iterate through the subgrid to see if we have 8. So the current formula that we have to calculate where the row of the current subgrid starts and the column starts is, let's say start row, I'm just going to say SR is equal to current row, it's row over 3 times 3. So how does this give us the start rows, index of the start row of the subgrid? So the current row that we're at is 2. That's for the cell of value 8. Divided by 3. That's an integer division. What's this going to give you? It's going to give you 0. Times 3. What's this going to give you? This is going to give you 0. And then we already got 0. Sorry, this should be 0, 0. We already got 0 for the start row, and now we do the same thing for the start column. What's the current column that we're at? We're at column 2. It's the same calculation. 2 over 3 times 3. 0 times 3 gives us 0. So in the end, we're going to get 0, 0, representing the start index of this grid that we're at, the start cell of this grid that we're at. Now, it works for all the other grids on the board. I'm not going to do the calculation for all of them. Please try it out if you want to make sure. So let's dive right back into the code. All right, so what we're going to do now is we're going to iterate through this entire subgrid. So we're going to say int, I'm just going to do L for row and M for column. So is equal to 0. L is less than 3 because subgrids are 3 by 3. L++. And then we do another one for columns. We call it M is equal to 0. M is less than 3. M++. Now we're going to have a very lengthy condition that checks whether we've seen this particular number in the subgrid while iterating through the subgrid. But we have to make sure that the cell we're currently iterating through in the subgrid is not the same cell as I and J. Because what happens is, while we're iterating through the subgrid, there's a very high chance that we're going to come across this cell, I and J, and we want to skip it because we've already checked it, right? It's the same thing we're looking for. We're looking for something repetitive. We're not looking for the same thing. So we're going to say if I is not equal to subgrid row start plus L, that's the current row that we're iterating through in this subgrid. And we do the same thing for the column. J is not equal to subgrid column start plus M. And the board at this cell in the subgrid, if it's equal to this number, if it's equal to the board at this number, then we know that this value is duplicated. So we can say board at subgrid, I'm just going to copy this, at this row in this column, subgrid column start plus M, if it's equal to board of I and J, then we know that this particular number is duplicated. So we say we've seen this character, and then we can just return false. That's it. That's how you solve this question. So if we've gone through all of this and we did not find a number that's duplicated on the rows, the columns, and the subgrids, then we can just return true. So figure out where this ends and just return true. Now let's run this, make sure everything works. Cool, it's accepted. I'm going to submit this, and then let's see how fast it is. All right, so it's faster than 36% of the submissions, and it ran in 5 milliseconds. Now let's do the second way, which is a little bit slower, but it has fewer lines of code. So I'm going to comment this out, all of this here. I'm just going to comment it out. And the second way to do this is to enumerate every single box. So every single subgrid, we can enumerate it with this formula. So let's say int box index, that is, it's very similar to the previous one. So row divided by 3 times 3. Now we're going to add column divided by 3. Let's see how this works. Okay, this is all going to be over soon. I promise you just a few more minutes and you'll be done with this. So if we're enumerating every single subgrid, this is going to be subgrid 0, subgrid 1, subgrid 2, all the way to the 9 subgrids that we have. This is going to be subgrid 8, right? 7, 6, 3, 4, 5, etc. Now we want to enumerate this subgrid. We want every single cell in this subgrid to be enumerated to 0. So cell has information of rows and columns, and this is the formula that we're using. Now let's apply this formula. Let's say we were at 8 and we want to know that we were at subgrid 0. So what we do is, what's the current row that 8 belongs to? Current row is 2. So 2 over 3 times 3 plus what's the current column that it belongs to? Belongs to column 2 over 3. So what's going to happen is 2 over 3, integer division, returns 0, times 3, returns 0, plus 2 over 3, 0, so this returns 0. So now every single cell in the subgrid, when we apply this formula to it, returns 0. So now we know that every single cell in this subgrid belongs to subgrid 0. The same applies for all the other subgrids as well. So that's it. If you want to try it out, which I really do advise you do, try it out for a few other subgrids and cells and see how it works. So back to the question. Now we do the same thing. We update how many times we've seen this number in the subgrid. So I'm just going to say box, because I've been using subgrids and boxes interchangeably. So please know that I mean the same thing when I say subgrids and boxes. So boxes, that's the hash map that we created. You'll notice that we haven't used it since. So box index of this particular subgrid, we're going to put this number, and boxes of box index that get or default. And then in this if condition, we can just add an extra condition and say if boxes of box index dot get num is greater than 1, then we know that it occurs more than once in this subgrid, and then we can just return false. I've commented this code out, so it's not, this one here is not going to be run, and let's try this. All right, cool. Accepted. Let's submit this and see how fast it is. Oh, it's the same. They both ran at 5 milliseconds. Let's submit it again and see what happens. 3 milliseconds. Cool. Let's run this again. Let's submit it. All right, this is exactly what I was looking for. So for some reason, the one with the hash map that's supposedly has the constant lookup feature, when looking through the subgrid boxes, it's a lot slower than the one with just the loop that looks through the subgrid feature. So this is something that I noticed yesterday while solving this question, as you can see, and I just wanted to do it. I just wanted to point this out in this question. So yeah, if you're doing this in an interview, you may not have to do all of this. I promise you, if you just do this one, even though it's slower, as long as you can explain how you'd optimize it by doing this, that's totally fine. Again, I think there are many, many, many more ways that you can validate a Sudoku board. This is just my way. And yeah, so if you like this type of content, please consider subscribing to the channel. Comment down below if you have something to say, share this video around the YouTube community, and smash the like button for the YouTube algorithm. And I'll see you in the next one. Bye-bye.